Newton's understanding of gravity was good enough to allow us to fly from the Earth to the Moon, but it's kind of amusing to think that you can go all the way to the Moon and back using something that's ultimately just an approximation. Everything in our universe seems perfect, governed by laws that apply throughout, yet certain mysteries have remained unsolved despite decades of research. Why does time travel in one direction? What is the nature of reality? Why does gravity exist? Why does time slow down when we travel at the speed of light? These are questions that have fascinated us for millennia. What if I told you that gravity is a lie, merely a construct of the human brain? This might seem unbelievable, but that's exactly what the famous physicist Brian Cox recently claimed. To find out what's wrong with gravity, we need to go beyond Newton. The problem isn't so much what he understood, but what he failed to address. Newton's theory of gravity allows us to predict how things move under its influence, but doesn't explain why gravity exists or how it works. It just lets you calculate things. Newton knew this, and he essentially attributed it to God, saying that the most beautiful system of the sun, the planets, and the comets could only proceed under the dominion and counsel of an intelligent being. In other words, he provided the tools to calculate movements, but didn't explain the underlying reasons, leaving that to God. In the vast universe that surrounds us, there are mysteries waiting to be uncovered, among them the perplexing phenomena related to time and gravity, two fundamental aspects of our existence. Imagine a world where time behaves strangely, where it can slow down or speed up, and where the force that keeps us grounded might not be what it seems. This is the realm of Albert Einstein's theories of relativity, which offer a strange twist on our understanding of time and gravity. Albert Einstein, a name known to many, gave us a new perspective on the universe with his theories of relativity. His work laid the foundation for understanding how time behaves under different conditions, particularly when we travel at extreme speeds. It all began in the early 20th century when Einstein proposed two groundbreaking theories, the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, transformed our understanding of time and space. It tells us that the laws of physics remain the same for all non-accelerating observers, regardless of their motion. This theory introduces the concept of relativistic effects, including the famous notion that time can dilate or slow down under certain conditions. One of the most intriguing thought experiments to explain time dilation is the light clock. Imagine being inside a spaceship moving at incredible speed, close to the speed of light, with a beam of light bouncing between two mirrors perpendicular to the direction of motion. To an observer inside the spaceship, the light travels in a straight line, bouncing vertically. However, to an outside observer, the spaceship's high speed makes the light beam's path appear longer and diagonal. The speed of light is constant for all observers, so the light beam must appear to travel a longer path. The time it takes for the light beam to travel its path should be the same for both observers, but since the path is longer for the outside observer, it seems like it takes more time for the light to complete its journey. This apparent time difference is what Einstein called time dilation. Time slows down for the observer in motion relative to the stationary observer. This isn't just theoretical, experiments have confirmed these effects. For example, particles in accelerators like the Large Hadron Collider reach speeds close to the speed of light, requiring scientists to account for time dilation in their predictions and measurements. The special theory of relativity opens a world where time isn't constant, where it stretches and compresses based on motion, challenging our everyday intuition and revealing a universe operating far beyond common experience. Special relativity introduced the idea that the speed of light is constant for all observers, about 299,792,458 meters per second. This concept defies everyday experience where speeds usually add up when in motion. It's as if the universe has a built-in speed limit, the speed of light. Special relativity also shows that simultaneous events may not be simultaneous for everyone. If two events occur at different locations and you're in motion relative to those events, what you see as happening at the same time might not be simultaneous for someone else. This challenges our conventional notion of time. Time dilation, where time slows down depending on motion, becomes more pronounced as you approach the speed of light. Imagine two identical twins, one on Earth and the other traveling into space at a significant fraction of the speed of light. When the space-traveling twin returns, they will be younger than their Earthbound sibling. This twin paradox is a real consequence of time dilation. Special relativity also predicts length contraction, where objects moving at high speeds appear shorter to stationary observers. This effect is minuscule at everyday speeds but noticeable as objects approach the speed of light. Einstein's famous equation, E=mc², is a direct outcome of special relativity, showing that energy and mass are interchangeable. This principle is fundamental for understanding particle behavior at high speeds and the energy released in nuclear reactions. Special relativity isn't just theoretical, it has real-world applications. GPS systems rely on precise timing from satellites, which are moving relative to us and subject to time dilation. Without accounting for these effects, GPS would be significantly less accurate. Special relativity forces us to reconsider our notions of time and space, demonstrating that the universe operates in ways that defy everyday experience. Time isn't absolute but relative, influenced by motion. The constancy of the speed of light and the relationship between energy and mass are central ideas confirmed by numerous experiments. Now let's explore Einstein's general theory of relativity, proposed in 1915, which reveals a profound connection between gravity and the fabric of the universe. General relativity challenges the classical concept of gravity as a force acting at a distance between masses, presenting it instead as a consequence of the curvature of spacetime. To understand general relativity, think of the universe as a four-dimensional entity combining 3 dimensions of space and 1 of time. Massive objects like stars and planets cause the fabric of spacetime to curve around them, which we perceive as gravity. Imagine spacetime as a flexible fabric. A massive object like Earth creates a dimple in this fabric, causing smaller objects to roll toward it, analogous to falling under gravity's influence. General relativity explains the motion of celestial bodies in our solar system, predicting orbits correctly, unlike the old idea of gravity as an attractive force. A striking confirmation of general relativity came during the 1919 solar eclipse, when Sir Arthur Eddington observed the bending of starlight by the sun's gravity, matching Einstein's predictions and solidifying the theory's validity. Just as motion affects time in special relativity, gravity impacts time in general relativity. In strong gravity regions, time passes more slowly than in weaker gravity areas. Near a massive object like a black hole, your clock would run slower than one far from such an object. General relativity introduces the concept of black holes, regions of extreme gravitational curvature where nothing, not even light, can escape. The boundary around a black hole, called the event horizon, marks the point of no return. General relativity also has profound implications for the universe's structure. Initially, Einstein added a cosmological constant to maintain a static universe, but he later called it his greatest blunder when the universe was discovered to be expanding. The expanding universe forms the basis for the Big Bang theory, describing the cosmos's origin. General relativity also predicted gravitational waves, ripples in spacetime generated by massive accelerating objects like merging black holes or neutron stars. In 2015, the Laser Interferometer Gravitational Wave Observatory made the first direct detection of gravitational waves, confirming yet another aspect of Einstein's theory. Despite some alternative theories questioning traditional gravity, general relativity remains dominant due to its consistent success in passing extensive tests and explaining a wide range of phenomena. However, the statement that gravity is a lie highlights the importance of skepticism and exploration in science. Modified Newtonian dynamics, MOND, suggests gravity behaves differently at low accelerations, challenging the need for dark matter to explain galaxy behavior. Some scientists argue that general relativity is incomplete, proposing additional factors or forces. Skepticism and exploration are integral to the scientific method, driving further investigation and deeper understanding. While alternative theories are tested, general relativity remains the most successful due to its simplicity and comprehensiveness. Einstein's theories have practical implications, especially in space travel. The speed of light is the ultimate limit, posing challenges for interstellar travel. Time dilation means space travelers age slower than people on Earth. For example, a twin traveling to a distant star at high speed would return younger than their Earthbound sibling. Time dilation also affects technology, requiring adjustments in communication and navigation systems. GPS systems, for instance, rely on precise timing and account for time dilation effects to maintain accuracy. The unidirectional nature of time, known as the arrow of time, is linked to entropy, a measure of disorder or randomness. Entropy tends to increase over time, leading to the one-way flow of time. The second law of thermodynamics states that in any isolated system, entropy always increases or remains the same, creating the arrow of time. The arrow of time operates differently at macroscopic and microscopic levels. At macroscopic levels, we observe processes like melting ice or mixing coffee, where entropy increases. At microscopic levels, physics laws are time-symmetric, meaning processes are reversible. The arrow of time in the macroscopic world arises from initial conditions and complex interactions. The universe's expansion from the Big Bang, a low-entropy state, has led to increasing entropy, shaping the arrow of time in the cosmos. Quantum mechanics also plays a role, with wave functions describing particle probabilities evolving over time. Newton's grasp of gravity enabled humanity to achieve feats like lunar travel, yet it's ironic that a concept so fundamental remains an approximation. The universe operates under perfect laws, but profound mysteries persist despite decades of inquiry. Why does time flow in only one direction? What underlies the enigma of gravity's existence and its influence on time? These questions have captivated thinkers for millennia. Could gravity be an illusion, a construct of the human mind? Physicist Brian Cox suggests so, highlighting the need to explore beyond Newton's theories. While Newton's gravity predicts motion, it offers no explanation of its essence. He attributed this to divine order. In our vast universe lie many mysteries, especially those surrounding time and gravity, fundamental aspects shaping our reality. Enter Albert Einstein and his groundbreaking theories of relativity, which revolutionized our understanding of these concepts. His special theory introduced the idea that time and space are intertwined and affected by motion. Time dilation, a consequence of special relativity, challenges our common-sense perception, showing that time is not absolute but relative. Einstein's general theory of relativity went further, linking gravity not to a force, but to the curvature of space-time caused by mass. This theory predicted phenomena like black holes and gravitational waves, later confirmed by observations. Despite challenges and alternative theories, Einstein's concepts remain the cornerstone of modern physics, shaping how we perceive the universe's fabric and the passage of time. Newton's revolutionary insights into gravity paved the way for unprecedented advancements, including the ability to journey to the moon. Yet the irony persists, our understanding of gravity remains a mere approximation, revealing gaps in our comprehension of the universe's intricacies. While universal laws govern celestial mechanics, deep-seated mysteries endure despite rigorous investigation. Why does time appear to flow inexorably forward? What fundamental forces underpin the existence of gravity and its profound influence on space-time? These age-old questions have tantalized human curiosity for ages. Could it be that gravity, as acclaimed physicist Brian Cox suggests, is a cognitive construct rather than an absolute force? Cox's provocative assertion challenges us to reconsider the nature of gravity beyond Newtonian paradigms. Newton's gravitational theory, while adept at predicting planetary motions, falls short in explaining gravity's essence. Newton himself attributed its workings to divine providence. Amidst the vast expanse of our universe lie countless enigmas, particularly those pertaining to time and gravity, core components shaping our understanding of reality. Enter Albert Einstein and his revolutionary theories of relativity, which fundamentally reshaped our perception of these phenomena. Einstein's special theory of relativity introduced the concept of spacetime as a dynamic fabric influenced by motion, where time can dilate or contract depending on an observer's velocity. Building upon this foundation, Einstein's general theory of relativity redefined gravity not as a force but as the curvature of spacetime caused by mass and energy. This paradigm shift predicted exotic cosmic phenomena like black holes and gravitational waves, later confirmed through empirical observations. Despite ongoing debates and alternative hypotheses challenging established theories, Einstein's conceptual framework remains the cornerstone of modern physics. It provides a profound framework for understanding the universe's fundamental workings, from planetary orbits to the bending of light by massive objects.